Hello, my name is Andy Ruth and I'm a professor in the physics department at University College Cork. Our research concerns the development of instrumentation for atmospheric trace gas detection. The work is carried out in the Centre for Research into Atmospheric Chemistry, which is part of the Environmental Research Institute at UCC. The title of my presentation is Ammonia Sensing with a Gain-Switched Frequency Comb using off-axis cavity-enhanced absorption spectroscopy. Now that's a bit of a mouthful and I hope to shed some light on this in the next couple of minutes. I'd like to acknowledge my co-workers, Satish Chandran, Eamon Martin, Alejandro Rosado, Eric Soderholm, and Prince Ananda Raja from DCU, who all collaborated on this project, which was funded through SFI and Frontiers for the Future Award 8973, which I would like to acknowledge here as well. Why ammonia? Because ammonia is a hazardous, corrosive, colorless gas that occurs as a pollutant in the atmosphere in an agricultural setting. So fertilization with manure or slurry lead to significant concentrations of ammonia in the atmosphere and can cause a problem in rural areas. Natural sources are due to volcanic activity, but also it occurs in planetary atmospheres. The recommended maximum exposure limit for an 8-hour exposure is 25 parts per million by volume. So we use this as a target level for our instrument that we're trying to develop. The project objectives are based on two questions. Can a gain-switched frequency comb be used for off-axis cavity-enhanced absorption detection of ammonia? And what are the typical detection limits that are achievable in the near-infrared region of the spectrum for ammonia? So we are targeting the near-infrared region at around 1540 nanometers, where ammonia has a rich low-vibrational absorption spectrum. Unfortunately, the absorption strength, the integrated cross-sections, are not favorable in this region. They're quite small. However, gain-switched frequency combs work in this region. They have been developed for wavelength division, multiplexing, and optical data communication. And so we are trying to use some information technology and apply it to trace gas detection. Here you can see our cavity setup as we build it. And we're starting here with the frequency comb with a free spectral range of 100 megahertz. Now the light from this frequency comb is coupled into our absorption cell consisting of two dielectric mirrors with high reflectivity of 99.6%. And the light that goes into this absorption cell bounces back and forth many times and thereby increases the absorption path length over which the target species can interact with the light. The transmitted light is then collected and transferred via fiber to a Fourier transform spectrometer with which the spectra are actually measured. Now, as a little detail here, we're not going in on the axis of the optical cavity, but we're going off axis in the optical cavity. And that's done to make the approach more robust and to get rid of difficulties that are constituted by the mode structure of these cavities. And that's the reason for that. Now, the frequency comb is one of the key components, and we'll have a look at what that looks like. It consists of a slave laser and a tunable master laser, and what it outputs is a frequency comb spectrum shown here on the right. So it's basically a set of laser lines that are separated by 100 megahertz, which corresponds to the free spectral range. So each of these laser lines is essentially a pivot point in the spectrum that we're trying to measure and from which we want to determine the concentration of ammonia. So that's the frequency comb. And here are some results. So we use different mixing ratios of ammonia in air, 1 atmosphere of air, dry air, there's no water in there. And the comb we used had about 450 comb lines. Our integration time for these spectra that you see here is 20 seconds, and the resolution of the Fourier transform spectrometer is 0.15 wave numbers. So we have extinction coefficient versus wave number here, but you have also wavelength axis here. Now for these 4 different mixing ratios, we can see the extinction coefficient decreases linearly with the concentration as expected, and from extrapolating this curve, we can determine a minimum expected extinction coefficient of 12 times 10 to the minus 6 centimeters to the minus 1. This value translates into a detection limit of 15 parts per million in dry air at 1 atmosphere, and the whole done in 20 seconds. So this is smaller than the occupational health limit that I mentioned earlier. It's the 3 sigma limit. Now, the advantages of this approach is that no mode matching or locking of the modes to the cavity is required in the off-axis approach, so that's very good. And no tuning or scanning of the wavelengths is required, as in standard laser applications, because the comb constitutes a broadband light source. The drawback is that for a small free spectral range of 100 megahertz, the power of the comb is quite low, and it would be nice to have more power because we have high reflectivity mirrors and lose a lot of signal in that way. Now, in the future, we want to get rid of the Fourier transform spectrometer by using a so-called dual comb approach. So if we use 2 combs, we could get rid of the Fourier transform spectrometer and at the same time increase the resolution of the approach. Secondly, we also want to try and integrate these combs monolithically on a chip and to achieve high compactness, to make the setup smaller than it is at the moment. And through these 2 measures, we hope to achieve measurements of isotopes of these trace gases in the future and detect them with high resolution. With that, I'm at the end of my talk, and I thank you for your attention.